Welcome, everyone. All right, we have now Chelsea Voss, who's going to tell us all about Oneliner-izer.
Thanks. Is this on? Cool. Yeah, how many of you have programmed in Lisp or a similar functional programming language? Okay. You'll enjoy this, I hope. So this talk is about Oneliner-izer. Oneliner-izer is a compiler that converts Python programs into single lines, or one-liners. So in this talk, I'm going to talk about how we do that, what kind of transformations we need to make on Python code in order for that to work. And I'll talk about building the compiler, and hopefully give you an understanding of how this works. And we'll see some obscure details of Python along the way that maybe you wouldn't otherwise have had cause to learn. So I hope this will be fun. Let me give you kind of understanding of why I went about this. So there's this thing called the Python Bee at MIT. And the Python Bee is this event that's held once every year where you have a bunch of people competing to spell out Python programs, character by character. So you'll be given like this problem. This is an example of a problem that appeared once. And you have to stand in front of the projector, not looking at your code, and spell out DEF space F dot dot dot. So that's fun, and a lot of people enjoy it. Here's an example of a program that you might spell out to solve something like this. So when I was doing this, I didn't really want to get hung up with new lines and tabs, because one of the things that can really kill you is doing a new line and then doing the wrong number of tabs in your code. So what if I solved it in one line? You can do this in one line, like so, with like a list comprehension and checking if false is in the list comprehension. By the way, this is equivalent if you aren't aware of the all built in. So that's pretty fun. But as the contest goes along, you get more and more difficult problems. Here's an example of a problem that might happen in some of the later stages. So this is something you might have to do. Estimate pi via random numbers. Okay, you can write, your nice imperative solution to this. Can you write a one-line solution to this? It turns out that you can. Like so. A bit more complicated than the one before. So this begs the question, if I can write this as a one-line Python program, can I write anything as a one-line Python program? The answer to this question is yes. Because, as you just saw, you can convert it to a string and then exec it. We're done. You can also do something like this with semicolons. So these aren't quite what I want to get at, though. So these aren't as fun as using lambdas and list comprehensions. So I'm going to define some rules for this challenge. We want to use list comprehensions as much as possible. List comprehensions, if you aren't aware of them yet, you can make mutations to values in your list and kind of filter over them. Lambda expressions allow you to define functions in line. So my rules are going to be, I have one line, no new lines. I have no semicolons in this line either. I'm not using exec or similar tricks. And that's kind of what encapsulates kind of the aesthetic that I want to get out of this, where I'm abusing lambda and list comprehensions as much as possible. By the way, yes, this is terrible. Do not do this in your code, in case that weren't already obvious. Yeah, do you want to help with this? Thanks. Yeah, so this is what we're going to try to do. And this is terrible. But it's going to be fun, and we're going to learn things along the way. So some of the takeaways that we're going to get out of this. This challenge is solvable. You can actually do it. Lambda calculus is one of the things that allows us to do it. And some of the obscure Python features that we're going to see help as well. I've built a compiler that implements this called Oneliner-izer. And finally, as another reminder, do not use this as a software engineering paradigm. All right, so from here on out, I'm going to teach you about how we implement each of the features. So we'll have simple code blocks We'll have some control flow structures, and then we'll have some of Python's other features like import and try except. Okay, so as a first challenge, how can you convert this into a single line? You can think about this for a second. So one initial way you might think is to just replace everything in line. Replace z with y plus y, replace y with x plus x, and then you get this giant 1 plus 1 plus 1 plus 1 thing. This is suboptimal not only because of the exponential blowup, but also because of what happens if x equals raw input, for example, where we're calling it multiple times. So this won't be something that we want. Instead, this is what I'm going to do. So what we want is to print z plus z, but before that we need to know the value of z, so we enclose that in a lambda. Before that we need to know the value of y, so we enclose y, the lambda for that. And then lastly, we get our value of x. And by the way, there's an alternative method of doing this assignment to variables written down below. If you don't want to use a lambda, you can also use a list comprehension to set the value of z, and then only take that single element of the list comprehension. All right, so now we have assignments, and we have some simple sequential code. What about functions? What if we have function definitions in our code? So here we have f, for example, being defined, and then later on we go and use f in some computations. How can we do this? This is actually pretty simple as well. We just need to set the value of f, and the value of f is a function, and we can construct that function with its own lambda, using kind of the same techniques to build out that lambda if there was more code in there besides just the return statement. So that works. And by the way, this also works with star args and star kwargs, just as is. You can feed them into the lambda and it works, right? Another thing that we might want to do is functions that don't assign anything to a variable. So far we've been assigning things to variables. Say do something is this function that has a side effect. What can we do here? Well, one of the things that we can do is to take the return value of do something and funnel it to an unused variable. So we get something like this, where the value of do something goes to underscore, whether it's none or whether it's something else. That also works. A second technique that we might use, here we have a tuple where we do something as the first element of the tuple, and then the return value is the second element of the tuple, and we only take the second element of the tuple. This will also work, and it will correctly discard the data that we don't need from do something, its return value. Okay. So kind of the final thing in this simple code blocks section. Oh, by the way, all of my examples so far have been finagled so that there's a print statement at the end. Now that we can do functions with side effects, we can define our own print function and use it in the same way that we're using do something here. So we want to get a function for print. In Python 3, this is easy because Python 3 already has its print function, and we can use it in the same way, and this will work just fine. In Python 2, it's going to be a bit more complicated because we don't have that built-in print function. And if we try to insert a print statement into an expression, that's going to be a syntax error. In order to get this print function, you might think that we can do from future import print function. And actually later I'll show how we can do imports in this one-line code. But this won't actually work because this isn't an import statement, it's a compiler directive, and it has to have exactly that form in order for the compiler to read it correctly. Instead, what we can do is use the dunder built-ins and take the value of print from dunder built-ins and feed it to this dunder print that I'm defining. And so from here on out, I'll be able to have a print function. Okay. The last thing in this simple code block section is classes. Classes are other things that we might want to define as we're going through our code. This can be done using type. So I can set the value of the variable capital person to this type, which has a name, and I specify what things it derives from. I specify its built-in methods, and so on. Cool. And if we put it all together, kind of a reminder of how this flows, we work from the bottom up. So first I have something that has setting the value of y, and it also uses the return value of this entire block. In this case, this entire block returns none. And then I go up from there, adding each of the statements. So I have the print, I have the definition of f, and I have the definition of x, and so on and so forth. So this allows us to take big, long series of statements and convert them into one line. So far, so good. But all of our code is not going to be just these single lines of statements. Python has control flow, and control flow is useful. So let's talk about what we can do in order to implement if-else statements. So we have if-else statements. You have a branch, you have a Boolean at the top. Each of the branches might do something. They might call functions, they might modify state. And at the end, they return to the same line of computation and carry out some more stuff, in this case, a print statement. So you can think for a bit about what we might do in order to get this to work. The solution is going to use conditional expressions. So we have Python's blank, if blank, else blank. And then we're also going to use continuation passing. And I'll explain the continuation passing part in a second. As for the if-else, what we're going to do is have one expression for the first code block and another expression for the second code block, and then choose between them just like this. To figure out the code blocks, they have to be different things. So we're going to have to make each of them return to the end of the if-else at the end. So you might have something like this, where you have x equals 5, print x times 100 for the first, x equals 10, print x times 100 for the second. That's what we want them to do. We can't just write this, though, because this, again, is code duplication. And code duplication is going to cause exponential blow-up and make our programs really big if we have only a linear number of if-else statements. So in order to fix this, I'm going to take the duplicated part and abstract it out into its own function, which I'll call the continuation function. So here we have the continuation, which takes in all of the state that's been modified and does some stuff. And then each of our if-elses delegate out to the continuation once they're done. So the final result of this, applying the transformations that we've been seeing so far, is something like this. This is our if-else statement. And I want to draw your attention to what this looks like side by side with kind of this control flow graph way of visualizing how if-elses work. We have two different branches. We delegate out to one or the other, and then we return to the same point, and that point is our continuation function. The next thing to talk about is while loops. So I have a while loop. This is an example of a while loop. We have some initial stuff. There's some stuff that's in the while loop, and then there's some stuff that's after the while loop. What if we want to convert this to a single line? The answer for how to implement this is going to be conditional expressions and continuation passing, just like with if and else, but there's going to be some tricks. So if you look at the control flow graph for a while loop, it's kind of reminiscent of the one for an if-else. You have these two branches, and one has to go to the end, that's the false branch, but then this true branch has to wrap back around to the place that you started at. So the while loop needs to be its own continuation. We're going to have this recursive structure where we have a function while loop, and if the guard on the while loop is true, we call it. Otherwise, we carry on with the stuff at the end. So this while loop function needs to be recursive. This is problematic, though, because we've been using lambda functions, and lambda functions don't receive names until after they're defined. But we want this while loop function to be able to call itself. It doesn't have a reference to itself to point to. So there's a way to solve this, which is to use the Y combinator, which is a combinator that you can use in order to implement recursion on these anonymous functions or lambda functions. The Y combinator is also called the fixed point combinator, because if you take YF, it returns you some value such that that value is equal to f of that value. So YF equals FYF. And this is what enables us to create a function that can call itself. here is an implementation of the Y combinator in Python. And here is an implementation of this while loop in its final form using the Y combinator. This is kind of tricky. You need to pass to the Y combinator a function that has two arguments. The first one is a putative value of the while loop, which will be called later on in the recursive part. And then the next value is whatever the function should take in. If you want a good walkthrough of how this works, I recommend this Wikipedia article to you. It's pretty good to read. So that's while loops. So now we have if-else, we have while loops. We're doing pretty good on the control flow front. One note that I want to make is that so far we've been storing state using this lambda trick that I've showed you earlier. This is problematic once we start to define while loops, though, because our continuations need to take in as input everything that's been modified so far. And if you have a while loop that modifies a bunch of variables, or if you have an if-else construction where one of the branches modifies a bunch of variables, your continuation is going to need to take in all of those variables that were modified. So you have X, Y, Z, and the rest of the kitchen sink. In order to make this smaller, we're actually going to use that list comprehension trick instead. And we're going to use a dictionary to store the values that were modified. Fun fact, you can use a position in a dictionary as a thing in your list comprehension like this, but you can't do that with a lambda. So we can modify in place the value of the dictionary in this list comprehension. And this allows us to store state in a dictionary. So instead we'll have something like this. And we'll mutate the dictionary as we go through. And then I can initialize the value of the dictionary using locals to make sure that it has all of the local values. And a bonus of this is that if we're mutating locals directly, now you can import from one-line programs. So you'll have this ridiculous one-line program that's like a bunch of lambdas. It doesn't look like something that you can import from at all, but you're able to import from it. Preserves functionality. Next thing after while loops is for loops. Maybe we have something like this where we're going through an iterable. An important thing to note about this is that you can't always index into the iterable at some particular value I, but you will be able to consume the values one by one. For example, if I have an iterator that's a set, I can loop through that set just fine, and it'll print out the values, but I won't be able to access a particular value of that iterable. So in order to implement a for loop, we're going to need to take this into account. The solution for the for loop is something like this, where we use the next function in order to get the next value out of an iterable. And we also use a sentinel so that once you reach the end of the iterable, you won't throw an error, because we don't have try except implemented so far in this presentation. So this allows us to do that without having to catch errors. So now we've reduced the problem of for to some stuff that we've already talked about. We have while, we have if. We're done. It's good. Okay, let's talk about some stuff kind of beyond, like other Python features. Let's talk about imports. So imports are important. You want to be able to import modules into your program, use things like random or math or whatever library it is that you're using in this file that for some reason you want to convert to one line. We can do this. You can use the dunder import function in order to import a module by name, like so, and set that to the variable name that you want the module to be at, and then this will work. Import itself doesn't need to be imported. Raising errors. This is also something that we can do on one line as a Python expression. So say we want to raise the error bad. It turns out that generators have this convenient method throw. So that works. Similarly, if you want to do an assert statement, where you assert something and then you carry on afterwards, this is just an if, where if that's correct, then you carry on. Otherwise, you throw the assertion error. So that's good. Try except. Now we're getting like really into the nitty-gritty of things. And this is actually like a PyCon exclusive. This was not implemented the first time that this appeared on the internet and people saw it. So try except is kind of new. So we have try, we want to carry out some function. Except bad, that's like some error that might be thrown. If we want to handle the exception using the function bar. How can we do this in one line? This is pretty tricky. You just don't think of try except as something that you can do in one line. There is a way to do this, though. And the way that we're going to do this only works in Python 2 because it was deprecated in Python 2. We're going to abuse the context manager protocol in order to try and accept for our errors. So first thing I'm going to do is to define this handler that will handle the bad error and carry out the function that we want to do on it. And then we have this with statement at the bottom that carries out the foo function with the handler attached. We haven't implemented with yet, though, so I need to mess with that with statement in order to get it to be one line. So the first thing we're going to do is to move the foo function somewhere else. So we're moving it to this other handler body. Both of these are context managers. And we carry out foo there. Next, we're going to use context lib.nested and combine handler and body together. If you want to know why foo is in exit instead of enter, you can look up Python issue 5251. Finally, now that we've converted these to context lib.nested, we've created a way to take these things and make them into a context manager, just one context manager, which we can then enter and exit manually. And at this point, this is all stuff that we've seen how to do before. We can define classes, we can assign to CTX, and we can execute those methods on CTX. So to convert this to one line, here's the stuff from before that you would carry out. And this is the final result. Also implemented our else and finally, but I won't talk about those here. Great. So I've hopefully taught you a bunch of stuff about strange Python obscurities that you weren't necessarily aware of before. Things that are left, in case you want to try your hand at this, we haven't implemented from module import star yet. We haven't implemented yield and the associated generator functions that come with them. And we haven't implemented with statements. But we have built a compiler that carries out each of these transformations that I've shown you on actual Python files. It uses some of these packages in order to have its functionality. Most important of these are AST, which is used to parse the Python files into syntax trees, and symtable, which is used to figure out what scope some variables are supposed to be assigned to and prevent some very strange errors that might happen otherwise. And the code for this is here. This will also be at the end of the presentation. So you can play around with it, try to one-line your own files, and import things from them. Some caveats to this. Because we're implementing while loops and if-else and stuff like that as nested lambdas, we run into the upper limit to the Python parser, which is somewhere between 92 and 99. So if you try to execute a one-linerized Python file, you might get an error like this. This can be avoided by using PyPy. Another issue that you might come across, because we're implementing while loops using nested lambdas, not necessarily with tail recursion correctly built in, you might run into maximum recursion depth exceeded when you have very long loops. If you really want to get around this, you can set the recursion limit to be deeper. Yeah, so we've built this compiler. Finally, the last thing that you might think is, okay, you've written this compiler in Python. Can you convert your Python compiler to one line? The answer is yes. Yeah, and that's it. I'd like to thank the people who contributed code. In particular, Anders Kaziorg contributed many of these features and also some of the slides, and other people on GitHub contributed code. And here are some links if you'd like to read about this more or kind of try the demo, read about lambda calculus. Thanks.
Okay, we have time for some questions. Raise your hand and I'll bring the mic over to you. Okay.
Hi, thanks for tremendous talk. I got only one question. Why didn't you name it as Python to Lisp compiler?
Why did I?
Why didn't you name it as Python to Lisp compiler?
Ah, that would also be fun. It really needs like some of the details of Python in order to actually work in Python though. Thanks.
So I think I would actually consider the absence of wildcard imports to be a feature. However, with that said, what's stopping you from using the dunder all attribute of modules and then just for each and that import that from the module? Is it not defined in all modules or something?
I think from whatever import star is actually quite tractable. It's just that nobody's bothered to implement it yet. So, yeah.
Hi. Thank you for the great talk. That was
Yeah.
awesome. I have a question about your original constraints. So
Yeah.
you said that you wanted to use comprehensions, but if you're coming at this from Lisp, why would you not use map?
Why would I not use map? So actually a story is that originally I tried to implement for loops using reduce, where you would reduce over the iterable and apply the change to state to each step. That proved to eventually be removed when break and return inside loops were implemented. But yeah, map is pretty good.
Gotcha. Thank you.
Gotta raise your hand higher. I can't see that well.
For other weird Python features, are meta classes implemented?
Meta classes. I'll have to check.
Okay.
Yeah.
So this would be cheating quite a lot and Python version specific, but could you implement the with statement by building a function using the compile modules and build it out of Python bytecodes?
Using which module?
Compile it out of raw Python bytecodes and then call it. Since you can import those modules, it would be version specific, but we did have a talk earlier in the conference about bytecodes, so.
Oh, is this for implementing try except in Python 3 or implementing with?
No, for implementing with statements
Ah,
in Python 2 or 3.
I think I might
seems like
count that as
cheating, but-
executing strings. I guess it depends if you can do it without doing that.
Has this been useful in the Python B?
I won the Python B one year, but I did not execute code from this in order to do so.
Any
I
others?
would like to see that.
Okay, let's thank Chelsea for a great talk.